Image is an artifact that depicts visual perception. Data compression is a process of encoding information using fewer bits than the original representation. Image compression is a type of data compression applied to digital images. As the internet grows, there is a lot of data being transferred across it. Large telecom companies like AT&T, Verizon charge their users, that's you, for transferring data. It is usually by how much data is transferred. So, by sending fewer bits, there is a direct economic gain for the users. Also, the images on the web are loaded faster in the end user's device. This will cause more user retention and indirectly cause more economic gain. So, how do you compress images? There are two types of image compressions. Lossy compression can use transform coding, chroma subsampling, fractal compression, etc. Lossless compressions use entropy encoding, deflate, and predictive coding. In the ancient era of 1992, JPEG introduced JPEG. It stores data in YUV color model rather than RGB. Y is the Luma component, CB and CR are the chroma components. JPEG uses DCT. A DCT expresses a finite sequence of data points in terms of a sum of cosine functions oscillating at different frequencies. Here's what that means. This 8x8 pixel art can be represented by a sum of these 64 images, each multiplied by an intensity factor. Here, each of those images is represented with their intensities. Going from phase 1 to 64 phases, we can see it building a blurry picture and then a close-up picture and then finally a full picture. Now let's take a small portion from an actual picture. We can see that many of these are 0. If we reduce the quality, removing more phases, we get an approximate picture of the same thing. At a small enough scale, no one can notice. However, this does not work well with flat areas of an image. Even a small reduction in quality is easily noticeable. The other way JPEG can reduce its file size is by chroma subsampling. Human eye is super sensitive to luminance changes. However, it is not that sensitive to color changes. Changing the luma quality affects the image quality harshly, but reducing the chroma quality is barely noticeable. JPEG can reduce file sizes over 10 times with barely noticeable differences. Because it is so good, it has been used on the internet for over most of the time the internet existed. It is still the most used format because of its universal compatibility. It falls behind because there are better compression techniques now that provide better quality per byte than JPEG. So what's the new thing? It was unveiled by Google in 2010. It was based on an existing technology called WebP developed by Onto Technologies. WebP supports two types of compressions. Lossy works somewhat like JPEG but better. It is based on WebP8's intra-prediction mode. WebP8 divides the image into smaller segments called macro blocks. There are three types of macro blocks. There are four common intra-prediction modes shared by these macro blocks. Look at this picture. Let us take a small portion. Here, the algorithm tries to find the best match to its original pixels using various strategies and encodes it. One more thing that lossy WebP can do is lossy WebP can segment the image into up to 4 areas that have visibly similar features. For each of these segments, the compression parameters can be tuned independently, redistributing the bits where they are needed the most. Lossless WebP is a completely different codec. It uses various transform techniques, like predictor transform. It uses pixels already decoded in scanline order to predict the color of the next pixel. There are 13 different possible prediction strategies. Color indexing transform is used if there are not a lot of unique colors. If number of colors is below a threshold, those colors are stored in a table and referenced by their indices. Color gauge coding uses a palette of 32 recently used colors to reference the next scanline pixel. If there is no color match, the palette is updated. LZ77 backward reference is a technique where we can reference a previous sequence of pixels using the length to be copied and the distance of the start of the sequence. Here, using text instead of pixels, mad points to its previous occurrence, where mad points to its previous occurrence, and so on. The length and the distance are stored using LZ77 prefix coding as discussed in class. Some more transforms include color transform and Sabra-Green theorem. WebP uses arithmetic entropy encoding, achieving better compression compared to Huffman encoding used in JPEG. It's just better than JPEG in every way. Here's a comparison between WebP and JPEG. Clearly, JPEG suffer from terrible compression artifacts. WebP is so much better than JPEG. Also, WebP supports alpha channels. Transparency. But WebP is now 10 years old. The gains of WebP over JPEG are impressive but not evolutionary. So what's the solution? Version 1 of AVIF specification was finalized in February of 2019 by AO Media. It provides much better quality than WebP at similar byte sizes. It achieves this by using a new compression technique called chroma from Luma. Most image formats store brightness separately from color hue. AVIF uses the brightness channel to guess what the color channel may look like. They are usually correlated, so a good guess gives smaller file sizes, sharper edges. AVIF provides much better compression rates than both WebP and JPEG. Let's take the same picture from above. WebP looks better than JPEG. However, AVIF looks like it's in a different league altogether. AVIF is the next big thing in image compression. Support for AVIF is not good right now, but there are planned updates for all major platforms to support this format. All the references and tools used in this video are linked in the video's description. Thanks for watching. Until next time.